China's new additive makes concrete 40% stronger by doing something engineers assumed was physically impossible: bridging cracks before they even start. A single atom-thick sheet of carbon, spread through wet cement, is now producing compressive strength gains of more than 40%, using a dose smaller than the salt in a single pretzel. You heard that right, smaller than the salt in a pretzel. Most labs that tried this technique for a decade watched it fail, clumping uselessly the moment it hit water. And that failure is exactly where this story gets interesting, because the fix was not a new material at all. It was a completely different way of handling the one everyone already had. If a fix this small can solve a problem this old, hit a quick like and subscribe so you don't miss the next one. By the end of this video, you are going to understand exactly how researchers made an unusable material usable and what it now lets them strip out of every batch of concrete poured. Here is where the old ceiling starts to crack. For over a century, concrete has run on one simple rule: if you need it stronger, you add more cement. That rule is not a limitation engineers grudgingly accept, and it is a system they trust with their reputations. Engineers love cement because its behavior is almost perfectly predictable, batch after batch, decade after decade, on every continent. Manufacturers love it because the raw ingredients, limestone and clay, sit within a short haul of nearly every populated place on Earth. Governments love it because concrete is the cheapest way, per ton of load-bearing strength, to build a hospital, a dam, or a runway that will still be standing in 100 years. That trust was earned the hard way. Cement is made by heating limestone and clay past 2,600 degrees Fahrenheit, hot enough to melt aluminum twice over, until the raw rock chemically transforms into the gray powder called clinker. That clinker is the actual engine of strength inside every bag of cement sold anywhere on the planet. China alone produces more than half of the world's cement, more than the next several largest producing nations combined, because its economy has spent 3 decades building at a scale no other country has ever attempted. And here is the part almost nobody outside the industry stops to ask: if concrete is this reliable, this well understood, this deeply trusted by engineers for over 100 years, why hasn't anyone solved its biggest problem sooner? Here is a reframe worth sitting with for a moment. The very reliability that makes cement so trustworthy is also what has made it so hard to improve. Nobody tinkers with a formula this proven, because being wrong at industrial scale means a bridge that does not hold. Picture a chef who has cooked the same trusted recipe for 40 years, perfectly, every single time. That chef has almost no incentive to experiment with the one ingredient the whole dish depends on. Cement engineering has operated on exactly that logic for a century, and it worked. It is still working today, in nearly every structure you have ever walked through. But trust built on one unchanging ingredient carries a hidden cost baked directly into it. That cost was never really a mystery inside the industry. It was simply too expensive, economically and politically, for anyone to confront directly. And once you understand what that cost actually is, the real story of this video can finally begin. That hidden cost is chemical, not mechanical, and it sits inside the one step nobody can simply engineer around. Turning limestone into clinker releases carbon dioxide the instant the rock breaks down under heat, not from the trucks hauling it or the machinery grinding it. This is not about a dirty industry that could clean up its equipment. It is about a chemical reaction baked into the one material the entire structure depends on. Globally, cement manufacturing produces roughly 8% of all human carbon emissions, more than the entire aviation industry, every passenger jet and cargo plane on Earth combined. Each ton of ordinary cement releases close to a full ton of carbon dioxide in the process, meaning the industry's carbon footprint grows exactly as fast as the world keeps building. Here is the detail that changes how you should think about this problem. You cannot fix it the way you fix a coal plant. Switching to cleaner fuel does nothing because the emissions come from the rock itself, not from what is burned to heat it. For 40 years, the only real lever available was replacing part of the clinker with substitutes like fly ash or slag, and that lever had a hard stop. Push replacement passed roughly 60%, and the concrete's internal structure could no longer hold itself together, meaning 3 out of every 5 parts of every batch had to remain full-strength clinker, no matter how advanced the substitute material became. That ceiling meant an entire industry accepted an emissions floor it could not engineer its way beneath, decade after decade, project after project. The consequence was not abstract. Every government carbon target, every net zero pledge, every infrastructure budget on Earth ran headfirst into the same wall because concrete is not optional. You cannot build a hospital, a bridge deck, or a subway tunnel without it. So the flaw was not really about chemistry in the abstract. It was about an entire global industry with no honest way out, waiting on a material nobody had successfully deployed at scale. In poorer, fast urbanizing regions, that same ceiling translated directly into higher construction costs. Since every ton of clinker that could not be replaced was a ton of fuel, mining, and kiln time, nobody could simply skip. That material already existed, sitting quietly in electronics and battery labs, largely ignored by construction engineers who assumed it belonged somewhere else entirely. In 2013, researchers began publishing the first graphene oxide cement studies, data that was harder to dismiss than anything the field had seen before. That early research came out of labs scattered across China, Europe, and the United States, but it was Southeast University's Jiangsu Key Laboratory for Construction Materials in Nanjing that stayed with the problem after most of the field wrote it off. The core idea sounds almost too simple once you hear it. Take graphene oxide, a single atom thick sheet of carbon dotted with oxygen-rich chemical groups, and let it bond directly with the cement paste as it hardens. On paper, that should have worked immediately. In practice, it barely worked at all. Drop graphene oxide sheets into wet cement paste, and instead of spreading evenly through the mix, they clump together, the same way flour clumps into wet lumps in a bowl if you dump it into water, instead of whisking it in gradually. A clumped sheet of graphene oxide does nothing useful. Worse, it can create a fresh weak point exactly where engineers needed strength most. Here is what most people still get wrong about how this material is actually supposed to work. It was never meant to fill space. Picture chicken wire embedded inside a layer of plaster on an old wall. The wire is far too thin to stop a hammer blow, but it stops a hairline crack from spreading the moment one starts to form. That is the job graphene oxide does inside a cement matrix, once it is properly spread through the mix instead of sitting in useless clumps. Its oxygen-rich surface bonds chemically with the cement's own hydration products as the paste cures, and its microscopic sheets physically bridge the countless hairline cracks that begin forming the instant any batch of concrete starts to set. Nanjing's researchers, working alongside related teams across Chinese universities, spent years chasing not a bigger dose of graphene oxide, but a properly dispersed one, treating distribution as the real experiment rather than the material itself. That shift in framing is the whole reason this technology survived the decade almost everyone else abandoned it in. And here is the reframe worth holding on to. The dosages involved were never large to begin with. Researchers were working with graphene oxide added at a few hundredths of 1% of the cement's total weight, an amount closer to a pinch of seasoning stirred through an entire batch of dough than any conventional construction additive. Getting that pinch to spread evenly, rather than clumping into useless flecks, was the entire engineering problem hiding behind a concept that sounded simple from the outside. The mechanism finally worked, sheet by microscopic sheet. The only question left was whether it worked well enough to matter outside a laboratory beaker. Here is the honest limitation, stated before anything else. Graphene oxide's benefit inside cement is not linear, and it is unforgiving about dosage. Push the concentration much past its optimal point, and in tested formulations, the strength gains do not plateau. They collapse, sometimes falling below untreated concrete entirely. That is not a minor footnote. It means this technology cannot simply be added by feel, the way a contractor might eyeball extra water into a mix on a hot day. But here is what that number actually means in practice. Cement plants already run on precise, calibrated dosing systems for existing admixtures, adding plasticizers and retarders in fractions of a percent, batch after batch, without a second thought. Graphene oxide simply joins that same category of ingredient. One more precisely metered input among several a modern plant already controls. For an industry already built around exact dosing, familiar mostly means familiar. There is also an advantage almost nobody predicted going in. Compressive strength, the ability to resist being crushed, is the number every headline repeats. But in tested samples, flexural strength, the concrete's ability to resist bending and cracking under load, the property that actually determines whether a bridge deck survives decades of traffic vibration, improved by an even larger margin than compressive strength did. Engineers do not normally get a technology that overperforms on the harder property while still delivering on the easy one. Here is the detail that puts everything into perspective. The strength gains were never the most surprising part of this research. Durability was. Researchers at Wuhan University of Technology's State Key Laboratory of Silicate Materials for Architectures tested graphene oxide modified concrete against chloride penetration, the process that slowly corrodes steel reinforcement bars inside coastal and marine structures. Their tested formulation recorded a chloride penetration result low enough to meet the threshold for 100 years service life, a bar most conventional concrete never reaches without expensive additional coatings. That is the non-obvious application, hiding behind a headline about strength. Coastal bridges, tunnels, and marine infrastructure, where saltwater corrosion, not raw load, is what actually destroys concrete over decades. In those structures, a material that also happens to be 40% stronger is almost a bonus on top of the real prize, which is a structure that resists the specific decay mechanism that has quietly bankrupted coastal infrastructure budgets worldwide for generations. The question was no longer whether graphene oxide worked. The question was which industries would move first to use it. The lab numbers were compelling. What actually convinced the industry came from a cement plant, not a university. Working with the UK's Breeden Group, the Australian graphene manufacturer, First Graphene ran its own graphene-enhanced cement additive, PureGraph CEM, through full industrial-scale production, not a beaker in a university basement. The result, confirmed at plant scale, concrete measuring between 15 and 20% stronger in both compressive and flexural strength, enough that the head of the company was willing to say it publicly, on the record, to investors who would hold him to it. The field matched the forecast. That distinction matters more in this industry than almost any other, because a cement plant runs thousands of tons through a single mixing line every day, with humidity, aggregate quality, and mixing speed all shifting slightly, hour to hour, in ways no laboratory beaker ever has to account for. A material that only works under sterile lab conditions is not a material the construction industry can build with. Here is the detail that made adoption realistic rather than theoretical. The additive did not require plants to change anything about how they already operate. It gets introduced directly onto the conveyor belt, feeding the final milling stage, blending into cement that was already being produced, with no new equipment and no retooled process line. As one industry executive close to the rollout put it, the strength gain arrives without asking a single existing plant to change how it runs. If a plant-scale strength jump like that surprised you, The next part of this story is going to be even harder to believe. Hit subscribe so you are there when we cover it. It started with one application where strength per ton mattered more than the extra step of adding a new ingredient. Then, it spread outward from there. First into UK infrastructure work, and now through a July 2026 agreement to distribute the additive through the Sixth Element, a Chinese materials manufacturer based in Changzhou, directly into China's own cement supply chain. China produces more than 2 billion tons of cement every single year, a volume so large that the country alone accounts for roughly half of everything poured on the planet. The agreement was structured in stages: 200 tons before deeper manufacturing talks begin, 500 tons before local production starts, a cautious, verifiable rollout rather than a headline-only announcement. Every figure was publicly disclosed on First Graphene's own investor filings, the kind of document a public company cannot legally exaggerate without consequences. The claim now had receipts. Patent activity around graphene-reinforced cement did not stay academic for long. The first international filing on graphene oxide-reinforced cement and concrete went public in 2013, and it did not sit quietly on a shelf. These are not academic citations. These are legal and financial commitments. An international filing, published in early 2025, covering cement blends reinforced with three-dimensional graphene carbons at dosages as low as 0.05% by weight, shows the same underlying science already being locked down for commercial use nearly a decade later. In the United States, the battery and materials company Lyten filed its own patent covering graphene-enhanced cement, a sign that interest in this material has spread well beyond the construction industry's usual players and into companies that see cement as an adjacent market worth defending with intellectual property. In China National Building Material, the country's largest cement producer and the third largest in the world, has spent recent years investing across its entire low-carbon cement value chain, including carbon capture pilot plants and industrial waste substitution programs aimed at the exact clinker ceiling. This research targets directly Sonoma International, one of China's largest state-owned cement engineering firms, used its own 2026 technology showcase in Chengdu to unveil a suite of decarbonization systems aimed at the same industrial targets. Evidence that the pressure to cut clinker-linked emissions has moved from research papers into boardroom strategy at the country's biggest players. Here is the reframe that explains why all of this is moving now, rather than a decade from now. China has committed to peaking its carbon emissions before 2030 and reaching carbon neutrality by 2060. And cement, as one of the largest single industrial emitters inside the country, sits directly inside that target. In any market where a national carbon deadline is legally binding and a 40% strength gain arrives at a near-zero dosage cost, that advantage is not a trend. It is a competitive pressure no serious cement producer can afford to ignore. None of this activity is hidden behind closed doors either. Patent filings referenced here are searchable through the World Intellectual Property Organization's own public database, open to anyone willing to look, alongside the same investor disclosures that confirm the plant-scale results in the first place. What started as a handful of university labs chasing a stubborn dispersion problem is now something closer to an industry-wide race, with real filings, real dates, and real money already committed. Scale this technology across even a slice of China's annual cement output, and the numbers stop sounding like a lab result and start sounding like climate policy. China pours more than 2 billion tons of cement every year. Even a 30% cement reduction applied to a modest fraction of that volume could avoid carbon dioxide emissions in the tens of millions of tons annually, roughly the same order of magnitude as taking several coal-fired power plants offline for a full year. The secondary benefit is economic, not just environmental. The broader graphene materials market serving construction has been projected to grow from roughly $18 million in 2022 to more than $150 million by 2031, an industry expanding fast enough to eventually support the manufacturing volume, a market the size of China's cement sector would actually require. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets genuinely difficult. Most commercial cement plants do not yet own the ultrasonic dispersion equipment this process depends on, and retrofitting an existing production line is a capital project measured in years, not months. Building codes in most countries still have no formal category for graphene, modified structural concrete, and certification processes for new construction materials routinely take 3 to 5 years per jurisdiction. High-purity, single-layer graphene oxide remains expensive to manufacture at the volumes a national cement industry would consume. The dosage sensitivity that makes this material so effective also makes it unforgiving of quality control failures at plant scale, where a single miscalibrated batch could undercut public confidence in the entire category. And a certification earned in China carries no automatic weight in the United States or the European Union, meaning the same regulatory climb has to happen market by market, almost from scratch. Here is the reframe worth sitting with before the obstacles start to feel discouraging. Every one of these barriers is a logistics problem, not a scientific one. None of these challenges change what the science shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem as much as a chemistry problem. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the climate demands is a different question entirely. The story of stronger, lower carbon concrete is ultimately the story of what human civilization can build and where it can build it. Concrete is the material of hospitals, water systems, schools, and flood defenses, which means every improvement to its cost and its carbon footprint lands hardest in the places that need cheap, reliable infrastructure the most. Fast urbanizing regions across South Asia, Sub-Saharan Africa, and Southeast Asia are pouring more concrete this decade than almost anywhere else on Earth, often with tighter budgets and less access to the newest low-carbon technology than wealthier markets get first. That gap is real. A breakthrough validated in Nanjing, Hong Kong, and Changzhou will likely reach Shanghai and London years before it reaches Lagos or Dhaka, because certification and distribution networks follow money that already exists. What is genuinely new here, not incrementally better, but categorically different, is a relationship between strength and carbon that the entire industry assumed was fixed for a century, broken by a material added in a dose smaller than the salt in a single pretzel. That is not a minor improvement. It is a different category of solution. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the climate demands is a separate question, one that belongs to policymakers, investors, and manufacturers as much as it belongs to scientists. That is new. Concrete is not a niche material used in a handful of dramatic projects. It is the second most consumed substance on the planet after water, poured into nearly every structure humans build to survive, work, and move through the world, which means even a modest efficiency gain compounds into a genuinely civilizational shift over a few decades of ordinary construction. If a molecule too small to see can rewrite the relationship between strength and cement, it raises an obvious next question. What happens when that same nanomaterial science stops reinforcing concrete and starts replacing metal entirely? That is exactly the subject of our next video, on the material now measured at 8 times stronger than steel and 80% lighter. The link is in the description. If this changed how you think about what stronger concrete actually requires, Hit that like button and subscribe so you never miss what comes next. Turn on notifications. We publish every week. Now I want to hear from you in the comments. Should governments require graphene oxide class additives in public infrastructure projects now, before a full decade of real-world durability data exists? Or is it worth waiting years longer for long-term field verification before trusting it under a bridge or a hospital?